We are into our last part of the syllabus. Okay. Two things: static electricity, current electricity. These are the two things that we need to cover up. And after that, you're done. So what is static electricity? Electricity, made up of charges which are not moving, static, obviously. Current electricity is like how these things work. When charges start flowing, that's called current electricity. And after we deal with current electricity, we'll do some circuits, some basic circuits, and find out like about resistors and some of the circuit elements. Now, AP Physics 2 starts with this particular topic. So what you're doing right now is exactly how we start AP Physics 2. It's exactly the same thing. Except that maybe numerically it may go a little deeper, but generally it's the same thing. So in AP Physics 2 we start with this, go to circuits, and then slowly move on from there to magnetism and then electromagnetism and so on. But the foundation for whatever you're going to do next year is basically the same thing. So I will repeat the whole thing again next year for those who are like transferring from honors. So like this year I had 5-6 students from honors. They're doing pretty well also. Okay, this is chapter 16, and then we will cross over to chapter 18. 17, I'll just fly through 17 a little bit, just to give you the connection. But chapter 16 is on static electricity, chapter 18 is on current electricity and DC circuits, and pretty much it. 19. No, individually. Yeah, you'll have a test on chapter 16, you'll have another test on chapter 17.
We finished 16 fourth grade grades.
Yeah. It won't take much time. Alright, so let me give you some foundation on electricity itself so that you will have a better understanding. So, what was electricity thought of in the past? Initially, people thought electricity was a fluid that can flow from one place to another place. And how did they come to that conclusion? Especially when they fly kites, when they flew kites in bad weather, especially, they used to get something through the string. The string is generally wet, so something came through the string, and so they thought there is something flowing from above. There was flowing, so they thought it was more like a fluid that's flowing. So there was no other understanding about electricity. Okay. Now, people had no idea for electricity, but then slowly they started seeing some experimental evidence of the same sort of shock experience, the flowing experience. So when one object was rubbed on another object, they had a similar feeling. So of course they were not able to see any fluid right there, but they were able to get the same feeling as what they were feeling earlier. So that is how it all started. Electricity, the idea of electricity started off with simple experiments. Okay? So from a thought that electricity was fluids, later on people understood that it is not fluids. It is something else. And they discovered that electricity was created by friction. They discovered that electricity can be created by friction. So when they rubbed a glass rod, with silk, the glass rod acquired a property. The glass rod was energized. We call it charged. The glass rod is charged. The silk also appears to have a charge or getting energized. Something is happening in the glass rod. The glass rod seems to have an extra energy. That was a finding. And then later on they understood that similarly rubbed glass rods were seen to repel from one another. Similarly, rubbed glass rods were repelling against each other. All right, why are they repelling? And glass rod and silk, they are trying to attract. So they knew there were two kinds of electricity, but they didn't know what it was. They didn't know what was going on. So they said, okay, there are two kinds of electricity. One is positive, the other is negative. Because according to their convention, a positive will attract a negative. You know, opposites attract. Opposite genders attract. Not very a common statement these days, but opposite genders normally attract. Okay, so this one attracts this, and that's why they said positive, negative. And these are both positives, so like they repel. Like genders generally repel. Generally. You're not really fascinated. Girls especially, or women especially. Why? Because they don't like. Okay, I'm not going that far. I mean, there's always an envy, you know. Oh, they're better dressed. I don't like. There's always a kind of, I don't like that, you know, sort of attitude. Anyway, like charges repel. And unlike charges attract. This was considered to be the law of charges. So they discovered that kind of a law. They put out that kind of a law saying like charges repel and unlike charges attract. Again, what is a charge? Not known at all. They didn't have a clue what charge was. But they knew that something is happening, so they called it positive and they called it negative. And to this day, that convention stays. Now, if they had called this negative and this positive, then it would have stayed like that. So the names actually are given, and then it stays as a convention. Pretty much like North and South. Who named it? Somebody named it. Somebody wanted to give it a name in the English vocabulary, right? Somebody said, okay, let that be North and let that be South. So we are still using it as a convention. Now, if they had used different names, we would have been using different names. Simple as that. Now, someone who has no idea of English, will it make a difference for them, North and South? No. They have the same things in a different language. They're totally different. Just like that, because they didn't know what it was, they just said by convention, okay, positive, negative. A positive and negative can neutralize and can cancel. That's why they're coming together. Whereas a positive and a positive, there's no chance of cancellation. No give and take. And that's why they repel. All right? So this idea came up, and using this static charges, they could actually make current flow, because they could actually generate some kind of potentials, and they were able to have charges moving through wires. They were able to do electrolysis experiments because they were able to transport these charges and do something. And they had to give a unit for charge because they were able to see the consequences of movement of electricity. They wanted to give it a unit. And so the unit of charge is given the symbol Q. The charge is given the symbol Q. The unit of charge is Coulomb. Just a capital C. By the way, that is the SI unit. Coulomb is the SI unit. Of what? Of charge. They didn't know what that Coulomb was. How big the Coulomb was. They had no idea, but they just had to give some name, and so they gave it, all right, this is what Coulomb. What is a Coulomb? When you pass this much of electricity, you are able to get this much of mass settled on that plate, and so for 1 gram equivalent of this material, how much electricity, how many coulombs. So like that, they started defining a coulomb itself. So there was no other clear-cut definition. Okay, so they introduced the unit coulomb, and to this date we still use the coulomb. Now coulomb, by the way, is a huge charge. Coulomb is a big charge. 1 coulomb is a big charge. That if I keep 1 coulomb right here, you won't be able to stand next to it. We'll be electrocuted. It's so strong. So the charge of 1 coulomb is a big one. Therefore, we don't use 1 coulomb as it is normally. Normally, the units used are millicoulomb, microcoulombs, nanocoulombs, picocoulombs. That's how we use it. So although we use these, this is the SI unit. Okay. So if you're given some microcoulombs as a charge, you can't substitute that into equations. You have to take it as 10 power negative 6 coulombs. Okay. So these are prefixes that will be seen in front of coulomb because very commonly charges are very small. Charges are pretty small. That's why we use smaller. These 1 coulomb is a huge charge. Even though there is a SI unit, that's a huge charge. So if 1 coulomb is a unit of charge, Q is a symbol that is used for it. Now, it stayed like that for quite some time, and after that, the model of the atom got proposed. Different models, Bohr's model. Okay, so what is the Bohr's model? What's the Bohr's model of an atom? Yeah, what is the basic idea? There is a centralized nucleus, and then we have electrons around, right? So most of the atom is empty. And of course, Rutherford stepped in, did investigations using his alpha particle scattering experiments, and then he came to the conclusion that nucleus is very small, but it's positively charged. Electrons are outside. Most of it is empty. Electrons are on the outside, and electrons are negatively charged. So almost the same times, other experimenters were trying to do more work on these electrons. Sir J.J. Thomson, he studied the charge-mass ratio of electrons. Millikan's oil drop experiment, you must have heard about that in chemistry. Millikan's oil drop experiment. So Millikan studied hundreds of oil drops. He sprayed oil and got at least 1 oil drop, and because the oil drop was sprayed, it was already charged. And it came down, so he applied an electric field, and the oil drop was coming down under 2 forces mainly. One is gravity and the other is electrical force. And by equating them, he was able to actually calculate the charge of the oil drop. Okay. But charge of the oil drop is not for 1 electron, it's a bunch of electrons. But he repeated this experiment for hundreds and 200s of oil drops, and he got a bunch of answers. But what he found out from all those answers is all the answers were a multiple of a basic unit, basic number. So that is what he came up with, 1 electron. He found out that 1 electron has a charge of 1.6 10 power negative 19 coulomb. That's a charge of an electron. He came to the conclusion by studying hundreds of drops, and he found that all the answers he got for charge of the oil drop were multiples of a very basic number, which is this. So 1 coulomb is not a small charge. You can see that 1 electron is this many coulombs. So what is 1 coulomb equal to? How many electrons is this? No. 1 electron is 1.6 10 power minus 19 coulombs. So 1 coulomb is how many electrons? You don't have to worry about the negative sign here.
3.6 times 10 to the 19.
Seriously.
6.25 times 10 to the
6.25 times 10 to the power of 18 electrons. You can't just flip the sign here and then. Okay, I'll give you a simple example. One cake is $10. So $1. How many cakes? 1 over 10. 1 over 10. Or if you have 2 cakes for $10, then it'll be 2 over 10. You're going to. Yes, the unitary method. Alright, this is a power. This minus sign is just a power you can't do. Alright, so 6.25 10 power 18 electrons. That's a big number of electrons causing 1 coulomb. Alright. So when you rub glass rod with silk, what you're actually getting out is a couple of electrons. Not couple, bunch of electrons, but not this many. That's why if I rub glass rod on silk, you may have a charge on it of microcoulombs or nanocoulombs. So more understanding about charge was evident when they knew that the nucleus is positively charged. Why? Because there are, say for example, if I have 2 helium-4, what is the 2 standing for? The atomic number, which is the number of protons, positively charged protons. So the charge is 2 plus. What is the 4 standing for? The number of nucleons, protons and neutrons. And neutrons don't have any charge. And the number of electrons that are supposed to be around are supposed to be the same number as the number of protons. So if there are 2 protons, you are expecting 2 electrons in the cloud. That is, if the entire thing is neutral. Generally, everything tries to become neutral because they don't like to be remaining charged. So this is a neutral atom of helium. The same way, what is the charge on this right now? It is neutral. Why? Because there are as many electrons on this as the number of. So this is neutral electrically. What will happen if you knock off an electron? If you knock off one electron, then what happens is there are 2 positive charges, but there's only 1 negative charge. So overall the charge is positive. The charge overall is positive. It's like, imagine this classroom where there were 10 boys and 10 girls. And someone looks at through the glass. Someone looks from there and then see, look, what kind of a class is this? It's a neutral class, right? Now, if I kick 3 girls out, let's say the boys are positive and the girls are negative. If I kick 3 girls out, and then the next time someone looks into the class, what they will say is predominantly positive, which is boys, right? So that's basically the idea. So if more electrons are gone, then this thing becomes more positive. Okay. I got into trouble once in the Middle East because I used this example. I was teaching boys' school and girls' school. So in the boys' school, everything was okay. In the girls' school, I was going there to teach the girls, and it's the same topic. So I just kind of said, okay, 10 boys, 10 positives, and girls negatives. And when the girls are taken out, because boys can't be taken out, protons, positive charges, you can't remove them that easily. So girls taken out, that failed over there. They immediately revolted and said, why us? We are not negatives. Why should we be negatives? Let the boys be negatives. And so they started, they didn't let me teach. And so I said, okay, for the time being, girls are positive, boys are negative. Now the boys are going out. All right, so I had to change of course, not a big trouble, but just the fact that they were so sensitive to the simple fact that I'm calling this one as positive and that one as negative. You can't be so sensitive. Like positive, black, negative can be a trouble. If you're looking at it in a different angle, this will be red positive, black negative. Some of them can say, why this is negative? Why can't you just call the red one negative? Right? So there's always that confusion with colors. People sometimes call that racism. I don't know. All right. Come back to this. So you understand what is charging, right? So when can you say something is positive? So why is the glass rod positively charged? Because as you rub the glass rod on silk, the glass rod apparently has lost some electrons, and that's why it becomes positive. Silk, on the other hand, gained electrons, that's why it is. And if you take polythene, when rubbed against hair, now that is getting charged. Okay, so that's getting charged. Polythene rubbed against. All right. Polythene rubbed against. Polythene rubbed against hair. So you can see that hair is getting charged. The polythene is getting charged. Come on. All right. Yes, in these things. Sometimes it doesn't listen to me. I think it's because of the wind. Okay. That's the problem. See, I'm not supposed to hold it. Okay. Now it's done. If I'm touching the table, that makes a big difference.
Interesting. Was this the same like principle that makes like a balloon scooped like?
Yeah. Yeah. That's.
Pretty good. Like that. You have the same same shirt.
It's like a snake.
Different shirt. Same sweater. Different shirt. You're still on there.
The paper trying to get attracted. Yeah.
Is the paper hot, negative, hot,
Positive.
no?
The paper was actually neutral.
Okay, so.
Yeah.
Wait, if it's neutral, then why is it trying to get
That's what I'm asking you. Why is the paper? Why is the paper attracted? Anyone?
Because when you rub the polys on your hair, it loses electrons, and the positive charge of the
Actually, it's the other way around. So polythene is the opposite. Polythene, when I rub against this, against hair, I am losing electrons to the polythene. So the polythene becomes negative. And what am I then?
Positive.
I'm always positive. Okay. All right. So what is happening when I go next to the paper? The paper is neutral to start with. When I bring this negative charge close to the paper, the negative charges on the paper tries to run away from this, making one side of the paper positive. So therefore, it starts attracting. You understand this? So, huh?
Instead of your hair's lost all its energy, it's just this side's flat now, this side's like got
No, not the energy. All right. Now see, this marker right now is at rest. Now, hopefully, I'll be able to move it if I take it close to this one. Let's see. You see that? Let me record that. I'm just going close to it, and you can see what is happening to the marker is moving with me. There you go. All right. So what is happening over there is one side of the marker. So this is what? Negative. This is negative, right? So when I bring it next to it, the negatives from the marker move away from it, so making this side positive. So what happens is, because this is negative, this side becomes more positive than the other side, so it starts attracting. It's always going to be attraction. Right, Reed? Right. And I also shown you with the water. When water, I've shown you that, right, before?
Yeah.
I must have shown that. I can show it again. All right, let me take this there. There we go. Now, water is a polar substance, right?
Yeah.
Water is a polar substance, and so what happens when, since water is a polar substance, when I charge this marker and pen, look at that. You see how it was getting attracted? Why is it getting attracted? Because it's a polar substance. The positives and negatives will get rearranged, causing that. Wherever I take it to, so water molecules, the centers of the positives and the negatives will get separated. So when I take it right there, Drew, when I take this next to it, this is my pen is negatively charged. So the side of the water close to the pen is going to be positively charged compared to the other side. So that makes it get attracted. Of course, when the velocity is too much, it may show less of that. Okay. So you understand what is charging. When an object loses electrons, it becomes positively charged, and when an object gains electrons, it becomes negatively charged. Now we come up to the law of charges, Coulomb's law. Coulomb's law of charges. You can write this down. Write it down. The force of attraction or repulsion between two charges. The force of attraction or repulsion between two charges. The force of attraction or repulsion between two charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Coulomb's law states the force of attraction or repulsion between two charges is directly proportional to the product of the charges and is inversely proportional to the square of the distance between them. Have you seen a similar kind of expression anywhere here?
Gravitation.
Gravitation. In gravitation, the force of attraction between two masses is proportional to the product of masses and inversely proportional to the square of the distance between. See? Exactly the same thing. Also in magnetism, you'll be learning the same thing. Force is directly proportional to the product of magnetic charges, which is basically what is known as the pole strengths. So don't have to write it down now. Magnetic charges, which are pole strengths, and square of the distance. The inverse square law holds good. So if you try to look at it, gravitation, electricity, and magnetism, they all have very similar proportions. Combining these two together, F is proportional to Q1, Q2 over D squared. And we'll put a constant of proportionality, which is K Q1, Q2 over D squared. K Q1, Q2 over D squared. That is a proportionality constant. Now that K is not a constant, it is just a short form of writing it, but the actual K is 1 over 4 pi epsilon. This letter is epsilon. It's a Greek E. And what does it stand for? It stands for permittivity. And what is this term called permittivity? Permittivity is how well electric lines are permitted by the medium. Permittivity of medium. And what is permittivity of medium meaning? How well electric lines or electric fields are permitted by the medium. That's called permittivity. Now you can see this 4 pi and all that comes in because of the way electric fields get spread out. Just like the intensity. What is the intensity equation? Sound intensity. Power over 4 pi r squared. See that? You can see the 4 pi coming in. And that's one of the reasons why the 4 pi comes in. Because as this electric flux passes through, it is passing through a surface of area 4 pi r squared. Yeah.
Isn't like K, Q1, Q2 over like D, isn't that like lattice energy as well? That's
Energy, this is a force.
like in chemistry, is that the same equation with lattice energy? You know what that is.
But is the equation K Q1 Q2 over D squared?
I'm just wondering D. No, it's D squared. I guess it's the
It's the
exact
same thing, but it's just an attractive force.
How do you call it energy when you are supposed to call it force?
Well, it's like the attractive force between two ions.
It's like how easily it is for like way to like an compound.
So that's a force.
But they call it lattice energy.
Yeah. I mean, in chemistry, you call it different names. Physics, we do the real things. We do the real stuff. But in chemistry, sometimes we use some strange names and all that, and you can go on. But in physics, normally, like for example, the gas constant, the actual gas constant in SI units is 8.31 joule per mole per Kelvin. That is the actual answer for R. But I think you have used 0.0821 joule, 0.0821 joule mole, not joule,
Mole per atom. It's moles Kelvin per
atmospheres, liter atmosphere,
Yeah.
liter atmosphere.
Times Kelvin over.
No, liter atmosphere per mole Kelvin. Yeah, liter atmosphere over mole Kelvin, but those are not SI units. Liter is not an SI unit. Atmosphere is not an SI unit. Yes.
May you define permittivity?
Wait, what?
Permittivity.
Permittivity is the ability of the medium to permit electric fields through it. So that is how it is defined as. So it is a constant for different material. So epsilon is the permittivity of the medium. Now, the permittivity, if the permittivity of the medium, if it is for vacuum or air, permittivity, we call it epsilon naught. For vacuum or air, we call it epsilon naught. And what is epsilon naught? It's 8.85 times 10 to the power of negative 12. It's a fixed number. For vacuum or air, the epsilon naught is only one value, which is 8.85 10 to the power minus 12 Coulomb square over Newton meter square. That's a unit of epsilon naught. So what is epsilon naught? It's a permittivity of vacuum or air. So electric lines can pass through, electric fields can pass through vacuum or air with a certain ability, and this constant is derived of it. Yeah.
Is there just like a certain value you can plug in for K? Like can you like
We're getting there. So do you understand this part? Now, so for vacuum, what is K? K is equal to 1 over 4 pi epsilon naught. Now this is only for vacuum.
or
Yeah, or air. So if you substitute 1 over 4 pi times 8.85 10 power negative 12, and if you calculate it, you will get an answer for K approximately 9 10 power 9. That's an easy number to use. So unless otherwise stated, you can assume that there's no medium between. It's just like air or vacuum. So if I just blindly tell you, all right, there's a charge here, there's a charge, okay, it's air. So you don't have to worry much about it. You just use this constant. So 9 10 power 9 can be used straight away.
We don't use units for K.
Yeah, there is a unit which is the same, it's the reciprocal of that. Newton meter square over Coulomb square. That's the unit. But again, don't worry about those things. When you're plugging it in, your final answer, F, is supposed to be measured in what? Newtons. That's going to be newtons. Q must be in coulombs. T must be in meters. And K is 9 10 power 9. And you can find out the force. Now, just to give you an example, let's say this charge is a positive 15 microcoulombs. And this one is a positive 25 microcoulombs. Microcoulombs, very tiny. And if the distance between them is 50 centimeters, what is the force between them? Is it going to be attraction or repulsion? Repulsion. So, when you're using this equation for force, you don't have to put positives or negatives at all. Okay, just take the numbers. Just take the magnitude. Whether it's attraction or repulsion is first decided by looking at the signs. If it is both positive, it's repulsion. If it's both negative, it's repulsion. If they are opposites, then attraction. Substitute. K, 9 10 power 9 times Q1, 15 micro times 25 micro over what? 0.5 square. Remember to change it from centimeters to meters. I said everything should be in proper SI units. Calculate this and let me know what you get.
6.75 newtons.
How much?
6.75 newtons. Oh, wait, no, not hertz, but, okay.
13 point something. 13.5 newtons. 13.5 newtons. It's almost the mass, the weight of this book. So even though it is such a small charge, look at the force. It's pretty strong. Now what if these were millicoulombs? If this is a millicoulomb and that's a millicoulomb, it will be 13.5 million newtons. That's a huge force. So you can't contain 15 millicoulombs and 25 millicoulombs and in this distance, because the force of repulsion is going to be 13.5 million newtons. That's going to be a big force. So understand that electrical forces can be sometimes severely big. Alright, so you understand how to find the force. Questions? No? Alright. Now, if the medium is not vacuum or air, then what happens? The equation is different. If the medium is something else, so epsilon for paper, let's say is 4.0 times 10 to the power of negative 11 coulomb square per Newton meter square. This is for paper. Then what do you do? In the equation, you can't put 9 10 power 9 straight away. You have to use 1 over. But then instead of doing that, we can always connect this to epsilon. So what is this? The epsilon is going to change, right? So the K is going to be, the new K is going to be 1 over 4 pi epsilon. It used to be epsilon naught. Now it's going to be epsilon. You can rewrite this epsilon as 1 over 4 pi epsilon naught times epsilon r. Now what is epsilon r? It's called relative permittivity. Relative permittivity. So if I'm going to use relative permittivity, the new constant is going to be the old constant divided by epsilon r. So what is this whole thing? This whole thing is epsilon. So epsilon is equal to epsilon naught epsilon r. So what is epsilon r? The epsilon r is the epsilon divided by the epsilon naught. So what is the meaning of relative permittivity? Relative permittivity means how much bigger is the actual permittivity with respect to vacuum or air. So what do you do to find the relative permittivity for paper? Put that number 4.0 times 10 power negative 11 over 8.85 times 10 power negative 12, and you will get like 4.5-ish. So it's easier to say the relative permittivity of paper is 4.5 instead of carrying this number in here, right? So it's easy, just like humidity. What is humidity? What do you know about humidity? Do you know what is humidity? Do you use the word many times?
Like how much humidity,
Moisture's in the air.
yeah.
How much water vapor is in the air? In fact, it is the density of water vapor. Simple as that. You know what is density? So how do you find the humidity in this room? To find the humidity, what I need is I have to gather all the water vapor in this room and weigh it. So the mass of water vapor in this room divided by the volume of this room. That's the density. Humidity is the density of water vapor in this room. Is that how we measure? Is that how we talk about humidity? What do you talk about humidity as? Percentage. Percentage of what? Percentage of the maximum possible, the saturation. Like in this room, how much water vapor can this hold maximum? That is called saturation density. Saturation. That means this room cannot accommodate more than a certain amount of water vapor. You understand? So at this temperature, there is a certain amount of water vapor this can hold. So what we do is we measure the humidity in this room and compare with that saturation value. And then we find the percentage. So when you say, oh, the humidity today is 60%, what does it mean? It means the atmosphere around you is 60% of what it can actually hold. If you go to Arizona, they'll say 4% humidity. What does 4% mean? 4% filled up. The atmosphere is filled up only 4% in terms of water vapor. There's a lot of room. Yeah.
How did you, like, if we were going to measure, if they when they measure humidity, how do they gather up?
How do you gather up?
Yeah.
To measure it up? You can actually do the partial pressures and all that stuff. Yeah, you can use partial pressures. The pressure that is in this room is because of both the vapor pressure and the simple dry air pressure. Yeah, you can do that. There are different ways of doing it. Or you can actually weigh it in terms of, take a smaller sample. Don't take the whole thing. Take smaller samples. So if I bring a cold object here, like, a block of steel, I take it from the freezer and just leave it here on the table. What happens after some time? You'll see a puddle of water there. Where's water coming from? Not from the steel. It's just because the steel was cold, the water vapor that came close to it immediately reached the saturation point and immediately settled down there as water. And so it starts dripping as water. And once the water goes there, it will evaporate back again later. So there is a lot of water vapor in this room. So how we measure humidity is by percentage. The same way here, we normally talk about relative permittivity as an easier way of talking about this. Instead of really looking at this number, it's easier to say this. So what is the relative permittivity of glass? 2.5. What is the relative permittivity of this? Just by, numbers, yeah.
So would you plug in 4.5 for epsilon?
No. We put this in place of epsilon r. So what happens to your equation is this. Look at the equation. F is equal to, the actual equation is this. F is equal to 1 over 4 pi epsilon naught epsilon r q1 q2 over d squared. This is the actual equation. Now, this part is k. Right? That's your old k. 9 to the power 9. So basically what's happening to the force? It's q1 k q1 q2 over epsilon r d squared. So what is going to be the consequence of having some medium? You're going to have a number right here. You understand that? So what will happen to the force? Will it increase or decrease? Due to the presence of the medium, is it going to increase or decrease the force? It's going to decrease. Like if I have two charges in air, they exert a certain force between them, right? Now if I put paper in between them, isn't it paper now between them? What happens to the force between them? Bigger or smaller? Smaller. It goes smaller by how many times? Epsilon r times. Now the epsilon r for water is 81. What is the epsilon r for air? Huh? 1. Because air and vacuum are literally the same. So epsilon r for air is just 1. But epsilon r for water is what? 81. What does that mean? That the force between two charged objects, if water is between them, is how many times smaller? 81 times smaller. That is the reason why sodium chloride stays as a crystal outside, but when you drop it into water, it separates. Why are they separating into ions? When they were sodium and chloride ions are sitting together as crystals, nicely bond. What happened to all the bonding when it went into water? Water gets in between. When water gets in between, what happened to the force between them? Drops 81 times. So the force that's binding them becomes so weak that they start drifting off. So that is how ionization becomes. They start moving in as ions. Now in chemistry you may use some other terminologies, but this is the actual reason why the ions are separated. Why the ions? What do you learn in chemistry? Why is sodium chloride, when dropped into water, splitting into ions? What's the reason for that? I don't think you use the attractive forces at all. I mean, in chemistry, you don't use the term attractive forces. I think you talk more about
the forces between
energy
the
or something.
ions and the ions. If there is a force between, sodium chloride forces are weaker than the forces of water and ion. Like the water, solid, solvent, forces are stronger than solid, solid.
Okay. Anyways, now you know mathematically how many times different it is. So when water gets inside sodium chloride, the force between these two drop 81 times. Now what happens is the force between the sodium and the water, or the chloride and the water, they are very similar to the force here. And so they start drifting away. Right? So you understand the concepts of epsilon r. And so the actual equation is going to be this. Now, this is the actual equation where epsilon r comes in. But for very normal problems, you won't have this epsilon r. So don't worry much about epsilon r. If you're given some questions about charges, you just simply use that equation k q1 q2 over d squared, take ks. What? 9 10 power 9. It is not exactly 9 10 power 9, it's like 8.99 something, but it is nearly that, so you can just use it blindly for this. Any questions?